You can see. So it gives me great pleasure. This is our first seminar on behalf of the Texas A&M Energy to Lecture Series, our first seminar, and I couldn't think of a better start to the series with all of you here, and I would like a very warm welcome to Professor Nimir Elbashir, who comes from us, a colleague of ours from Texas A&M University at Qatar, and he is the director, the co-director of the Gas and Fuels Research Center. And I would like to, he will explain to us all about his long, well-established, well-known research in the area of natural gas. But I would like, before I start my formal introduction, to pass some material that we have. The Gas and Fuel Research Center is also a major partner of the Energy Institute, so we'll take this great opportunity to, first of all, a very warm welcome to Professor Elbashir before we start. Okay, so we pass some material for the center that you will hear more about it in a moment, and the exciting research opportunities and directions there. So can you pass some material in the back? Okay. I would like to say a few things about Professor Elbashir, who holds a joint appointment between chemical engineering at Qatar and the petroleum engineering program there. He is the director, as I said, of the Texas A&M Engineering Experimental Station Gas and Fuel Research Center. That's an activity perhaps not as many people should know about, but it involves almost 30 faculties around the Texas A&M campus and beyond, right? So he's also the chair of the Oryx Gas to Liquid Technology Excellence Program there. His previous research career, he started his career at BASF R&D Catalysis Center in New Jersey, and he's well known for his research in the area of advanced catalytic reaction, conversion process for natural gas, gas to liquid, CO2 capsule, and the like. He holds several US and European patents, and obviously he's well known for his large number of well-cited publications in journal, public conference, and technical industry reports. He has the recipient of many awards over the years, and I would just like to highlight that he has well-established awards from BASF Corporation, from ASCHE, and more recently, the Genesis Research Excellence Award for TIS in 2016, and the Faculty Excellence Award in 2017 from the Texas A&M University at Qatar. Without further ado, again, a very loud round of applause for Professor Elbashir.
Thank you so much, and it's my great pleasure and honor to be here again, and I am enjoying to see the growth of the Energy Institute. We recall a long time ago with late Chris Flodas how his vision now is still in reality, and Stratos and Kostas here is carrying on this vision to move forward. And as the director of the Gas and Fuel Research Center, as Stratos indicated, that this is quite relevant to the Energy Institute, and we'll be working together. It is my great pleasure to give you this seminar, and it will be a kind of movie, by the way. So I will gonna tell you a lot of stories. And those who are coming here hoping for a very technical kind of presentations where only figures and graphs and diagrams, they may not see it, but I will gonna touch on so many different areas. And I am around here until Tuesday, so you are most welcome to come by and discuss any of those topics if you want to go in details in any of them. But my story will start at the beginning to tell you, if I'm successfully moving those slides in the right direction. That's forward direction, I guess.
You need at least 3 professors.
So which one?
I don't know.
Can I use it? Because it didn't seem it's moving. Okay, so my talk will be divided into 3 different sections. The first one, I will gonna very briefly talk about the global energy market and the role that natural gas is expected to play, specifically in the United States and in Qatar. That's where I came from.
Okay.
And then I was gonna move, I guess we moved here further, yes. So then I was gonna talk about this model of Texas A&M Qatar. Where does it exist? Because many of you haven't seen it or haven't heard it. Nevertheless, some of the students here have an opportunity to work there and to spend time taking courses over there. And then I will come to very specific research area where we have a very big collaboration, global collaboration. And now we're going to give you an example of what we do in research in gas processing technology. So,
Okay, I think this is the one.
this is the one?
Please, this one.
Okay. So again, as I indicated, it is all about energy. Okay? And energy need global-wise, because I'm here in the Energy Institute, I have to make the story relevant to the Energy Institute. But if you look around, you're going to notice that by 2040, and all the way up to 2050, that's we're going to have an additional 2 billion human beings existing in Earth. But it's still the distribution of energy is still dominated by certain nations. I'm not sure whether, so sorry. This is a cursor here, but it seems there is no cursor. Okay, that's dominated by a developed nation over here. That's almost take over a significant portion of the energy need. But if we look at the energy distribution and how the energy market globally changed from 1970 2000 period all the way to 2000 to 2014, and then from 2014 to 2004 you're going to see so many different stories, because now in the media you're going to read a lot of news that France by 2030 we're going to stop diesel and gasoline fuels, and then followed by Germany, and then followed by Scotland. They said not 2030, 2032. I'm not sure about 2032, but if you see that the domination of energy is not by those nations, even though in terms of quantity they have a significant portion of it, but the growth of energy demand from 2000 to 2014 controlled mainly by China. China and the growth economically in China take a significant request in the global energy demand, and that's where the prices of oil get all the way up to $149, etc. Then the growth in China reaches the saturation level and goes down. And the market in the future will be distributed. China contribution will be much lower, and then India will gonna show up in the map. Okay? And also the United States will come back again to have a significant contribution relevant to the one that it really missed in the past. So this what really decide on what type of energy the global needs for the coming future. And if you look at crude oil, for example, we're gonna see still the domination of Saudi Arabia. Okay, but the United States become a major contributor in crude oil market, followed by the nation that we are very familiar with. And the growth of the market is quite conventional, and with all the expectation of reaching the oil hub, it's not happening. It's still the people moving forward on it. And that's, you see, that's still the central market for many of sources of energy and oil is coming from this part of the world, in Asia. And that's the overall exchange, specifically when we come to crude oil, global market. United States even now become the major producer. They are still receiving a lot of oil, gasoline fractions from different refineries and some of the crude oil. But our story here is mainly related to the natural gas. The natural gas is a different game. And its participation in the overall energy buy changed significantly in the recent years. So this portion is not the right portion. Okay, that's an old one. This is by 2010. And you will see later why from 2010 the whole story has been changed. But the natural gas become a critical player, competing with coal to follow the oil. And if we look around, we're going to see again the two countries of interest for us in the energy market, and specifically in the natural gas, they are present there. That small country that I will define later, Qatar, playing a critical role as producer, but as a net exporter directly after Russia. While the United States is still major producer, but locally used it is natural gas. So the natural gas expectation, that's it will keep playing a critical role, and the expectation that by 2040 that it will going to reach 40% of the global energy demand. That means it will be a significant competition even with crude oil. But who are the major players? Still Russia, have the world's largest reserve of natural gas, followed by whom, guys? North America. And the North America, the map is changing big time. The Middle East, those very few countries, and Qatar is a major player on it. That's when they say Middle East over here now, significantly in terms of real production is Qatar. Okay, specifically in terms of natural gas, you see they take a significant portion of the overall natural gas market, and mainly on the conventional natural gas. But in the United States and North America, in the conventional they are much lower than Russia and Qatar, but they are leading in terms of the non-conventional. So what is this non-conventional gas? Shale gas. Okay, and that's a game changer. That's happening. And if you look around in the US map, that's what's going to show you from 2006 to 2016, the order of magnitudes in growing of natural gas resources in the United States. Over here, how much order of magnitude? Growth 2,312% now. Marcellus field over here. And then when you come to Texas over here, okay, because you already guys, you have a lot of this natural gas, they are get used to it. It is relatively low, but here is a significant growth that's happening in the northeast, okay, and here is around 1,000 plus. So the shale gas is a changer in the United States. Nevertheless, the monetization of natural gas in the United States haven't changed much. And we have been in a workshop with Dublin last year in West Virginia. We're talking about what else, what next, guys? So with this shale gas and all of the success story you have seen over here, is it still the same old market? Because it's still the market in the United States is the local market. The market could still absorb all of these resources of natural gas, and if we look around, we're going to see no significant difference from 2005 in terms of the distribution to 2040. It's still industrial, electric power, transportation, commercial, and residential. That's still the same monetization. The distribution may slightly change in terms of the quantity, and even the growth in the quantity. That's even after almost 10 trillion cubic feet from 2005 all the way up to 2040, the distribution is still the same. Okay? And now, the story will be what will happen to the energy mix in the United States. What will happen is that this coal will gonna shrink, whether the political horizon want it to grow, it will never grow, okay? Because the competition of the shale gas will always be economically dominating. It cannot compete economically with the shale gas, so it will shrink even lower than this value, but now it will be only 18% from coal, 30% from crude oil, and 30% from natural gas. So natural gas is the future dominating of energy in the United States, okay? Now, still, there is no big deal in terms of what they were gonna do with this natural gas. And now, the whole horizon is focusing on sending it to the neighboring countries as liquefied natural gas, okay? And the potential that started from 2025, etc., that they were gonna build infrastructure that initially was to receive natural gas from Qatar in terms of LNG. Now it will be to export natural gas, and it will gonna go to Canada, Mexico, okay, and other places, okay, in the States, okay, and so on. So now the market will gonna keep changing in the United States, nevertheless it having until now. And the only source of other form of monetization is to convert it into liquefied natural gas. Now let us see the small tiny country, which is called Qatar, okay? And this Qatar is existing over here, to those who are not familiar with it, existing in this part of the world. Negligible in the map if you just look, okay? And by the way, when I have been in West Virginia, I was trying to make similarity because I was talking also to a big workshop focusing on natural gas, and I'm telling them the story of Qatar. So, and I know West Virginia is a very small, tiny state in US, so I'm trying to say, hey, this is an equivalent to you, but I found that West Virginia is 16 times, okay, Qatar. But this state is extremely wealthy because of these resources of natural gas, by the way. And that's make a huge shift in the economy of the state. That's in 2011 it make a record. That's only 2-digit GDP growth, global-wise. At that time China was in the hot and in the top of the peak about 9%, 8 to 9%, and Qatar almost 19%. Okay, now things goes down back again because of the oil prices. Nevertheless, what they have done is different from the United States, different from Russia. And that's what helped them even in the very tough political situation they are in right now. Because if they focus only in one monetization form, like building only a pipeline to go to the neighboring countries, okay, it seems like someone get in the middle from the online. Okay, anyhow, it's too complicated for me to handle. So what they have done, they haven't only focused on one monetization form of natural gas, which is only transportation by pipeline. They also look at building infrastructures in LNG. And that's LNG, make them the world leader in LNG by capacity, by the way. They have almost from 34 to 40% of the global LNG market. Okay? This is one of the disadvantages of the online thing, that you cannot control who is getting in the middle of the talk. And also they make significant
technology.
Yeah, that's it. That's part of the deal. That's part of the risk. They also make a huge investment in the chemical treatment of natural gas, and that will be the focus of my talk when I come later. That's converting natural gas into liquid hydrocarbon products. So when they get into a political crisis, okay, they still have a significant monetization form to keep them stable. They have no problem, because if it is only the pipeline, it will happen similar to what happened to Russia when they get into problem with Georgia and Ukraine. That they were going to close the pipeline, and then they will try to figure out how they were going to send the gas to Europe. Okay, but they figure out all these monetization forms, and that's helped them. So from a nation that's mainly have only source of economics in that peninsula, which is in terms of fishing and hunting for pearls, now these nations, because of such a kind of industry, move to the future. Okay, that's a huge, one of the world richest nation per capita, and I guess you know those are stadium for World Cup 2022 that they take from the United States. Okay, the final one. Okay, and this is a new airport, that's a huge one, but also they are contributing in terms of culture-wise. By news media, they have the very famous Al Jazeera news media, and a lot of events that's happening in this nation. That's because of that wealth of natural gas. Okay, so now let us move to Texas A&M Qatar, which is why Texas A&M existing over there. Existing is a part of a vision that's handled by Qatar Foundation. It's a vision of Her Highness Sheikh Moza bin Nasser Al Musnad. She's the one that built this structure of education from pre-kindergarten all the way up to PhD programs. And this structure, they invited universities from all over the globe, and specifically in the United States, they have been quite selective to target certain specialties in those universities. So they built a research center that's well equipped to facilitate those universities in terms of moving on towards research activities. And Texas A&M came in the engineering, and we came because honestly of the petroleum engineering. Okay, our petroleum engineering ranking very high, and that's one of the programs that we have. But we have Weill Cornell in the medical school, we have Virginia Commonwealth, okay, we have Northwestern in media and journalism, we have Carnegie Mellon in computer science, also biology, they have University College London, they have Georgetown University Political Science, etc. So they have different schools. So we came to Qatar to bring the heritage of this institution, and with all the culture that it has, and to create an environment that will integrate those students to live a similar environment like any Aggie that existing over here in any of the Texas A&M campus. And therefore we make sure to well integrate them, to give them an opportunity to live the same life. And we have an amazing building that those who visiting us over there are going to see it's something quite fancy, and we have a classroom well integrated with over here. Sometimes I teach my classes from here when I'm here. Sometimes I'm teaching classes from there to the student over here. But also we give the student an opportunity to live the same Aggie lives, and they come here, they spend semester or a couple of semesters, they do the graduation project together with their colleague. We have many students coming from the main campus, spending semesters over there, they take the same courses, the same curriculum, everything is identical. Okay, that's an statistics on all the statistics, but almost the same now. So in terms of undergraduate students, we have 550 for engineering program, chemical, petroleum, mechanical, and electrical, okay? we have very strong presence of female, that not even in the United States existing, almost above 40% of our student body are female students, and they are doing quite well, by the way. So, what we are supposed to do, we are supposed to train highly skilled engineers and to give them an opportunity so that they can take the lead in those infrastructure that Qatar have the most advanced in the world. And what we have done, we mainly focus on how to maneuver our program to be extremely selective in a way of handling certain topics as of relevance to the economy of Qatar. And natural gas, obviously, is the core of those fields. So those undergraduate students, they work from research, starting from the freshman and junior. I have in my lab now around 12 undergraduate students from different disciplines, and they do research work, and they write proposals, and they get money. So the money that they get in writing those proposals, this is from the undergrad only, is above $300 or $3 million. Okay, now I believe it exceeds almost $5 million. They write proposal. After the very second year, they start writing proposals, submit, and they publish paper, and they do a lot of things. Okay, that's it. They come to conference in the United States and around the world. Another feature that our success story in moving this program only from engineering program to research institution have been well recognized global-wise. So in the ranking of 2015, I guess, the THE, that's Texas A&M Qatar, has been ranked as #1 in the MENA region. MENA, Middle East, and North Africa region. And you have there universities of thousands of years existing over there. Okay, and then hundreds of years, many of them, but we have thousands of years in Tunisia and in Morocco, in so many of those institutions. Why? Because in terms of magnitude, we are very small faculty, but the magnitude of research contribution has been very well recognized. Now we come to this Gas and Fuel Research Center story, okay? So, what is really happening in the United States, and the booming happening because of the shale gas, and the success story we have in Qatar that you're going to see later in the third section of this presentation, made it very clear the need that we establish an entity of multidisciplinary faculty and professors that work together to speed up the technology development in the area of natural gas monetization. We have a lot of lessons we learned from Qatar in terms of the growth and in terms of experience in the United States is well established. So the expectation that the United States chemical and other industry growth by 2030, which is very close, okay, is around 110 billion. That's a very rough estimate. But this would never be happening, okay, unless we speed up technology development. So we build huge facilities in Qatar, okay, to support all of the different projects I was going to highlight, but also here we have a heritage of research and expertise, and we have huge facilities. So how to integrate them in order to advance this technology development? Those are some of the, I'm missing one of the colleagues over here, that's the members of the research center from Qatar side, and you can see that some of the top-notch professors, Ragomir Bakouri, he just retired, is a world leading figure in the area of Fischer Tropsch chemistry and catalysis. You have Ken Hall in hydrocarbon processing, okay, as well as from mechanical, from petroleum, okay, from different fields. And when it comes to college station members, and I believe also I'm missing a couple of them, Bablina, okay, I was trying to reach you to get the photos on time, but we couldn't. But you can see that it's a blend of chemical engineering, petroleum engineering, mechanical engineering, material safety, and we are all aiming to work together, and they are the top people in the world. They are the best in what they do, okay, to speed up this technology development. And what we mean by technology development is starting from the exploration all the way up to the final products. How to sell the final product. So in the production sites, how to get this shale gas, how to use it, how to make the whole process safe and easy, and how to improve the enhancement in the process. In the treatment of the natural gas, we call it midstream oil and gas, and that's the course I teach for the students here in the Executive Energy Program. You're going to see me later in February, mainly focusing on this area. And then in the downstream side, when we go to LNG, to DTL, chemicals, direct conversion, indirect conversion, and then finally when we get those products from natural gas, how they could be really competing in the market. And all of those are the projects that we focus on. We work with a global entity. Our purpose, similar to the Energy Institute, and therefore there is a very strong synergy. We educate people, we prepare highly skilled engineers, researchers, technical staff, but at the same time, we should have a global impact. And that's global impact, both to the state of Texas, over here to Qatar, as well as global-wise. Okay, how we are doing our work? We are very selective. So when we even envision how to collaborate with industry, we hadn't called for a conventional consortium and we tell them, hey guys, you have to pay for the following, and we were going to give you the following, or you were going to join a consortium, whatever. We have been extremely selective to work with the world-leading industry in specific areas of interest. We know what they need. We either formulate a collaboration with them that's funded by a third body, but they put some money on it, or they completely funded one of those areas. And we hunted them one by one. Okay, and we use the depth of the expertise we have it here in College Station to move forward. There are so many projects here, I don't want to waste your time detailing. Now, all of this is introduction. It's a very long introduction, all right? So now let's come to business. Let's talk about a very specific natural gas processing field, and I also will be very selective because my time is not gonna be sufficient. It shows you when we go in one example how we could really make a difference. Even to some that at the commercial level that difference might be small. And I will be mainly focusing on this technology, gas to liquid technology. If we converted this natural gas we have into liquid hydrocarbon products, what would be the potentials? What we could really do on it? And if we look at it, why we convert natural gas into liquid hydrocarbons? Why we just sell it as natural gas? Because here in US we need it as natural gas, or sell it anywhere else as LNG, as natural gas, and let those guys handle it. Why? If you look at the specific energy density, you're going to see the significant difference between the liquid hydrocarbons and the gas in terms of the energy that you could really associate. But not only this, that the potentials of having a significant number of hydrocarbon products that associated with it. So how the process will going to look like? This is an actual plant, by the way, that existing in Qatar. We call it the Oryx GTL program. Okay, the Oryx GTL plant, it's a Sasol and Qatar Petroleum joint venture, Sasol technology. And this shows you how the process looks like, and I can use it because I am the chair professor of Oryx GTL Excellence Program. So I have the right to do that. So the process starts with natural gas. We reform it to make a syngas. We take it to a technology known as Fischer Tropsch. We make syncrude, liquids come here, this is the heart of the technology, and then we refine the liquid to get our final products. This is the technology. But this technology is not as simple as I have described. By the way, this is technology in 1920s. Okay? So what is really the issue with this technology? This technology is energy intensive process because you are converting gas into liquid hydrocarbons and you have to make sure that you make money out of it. Now a lot of people will be questioning making money out of it. If we look at the cost distribution, we're going to see the first step. Just converting this methane, natural gas, CH4, into carbon monoxide and hydrogen is almost 70% of the cost of the process. So we pay the heavy cost over here. Then we come to the Fischer Tropsch, which is also catalytic process from 20 to 24. And then finally the refining process is syncrude. Is a white crude relative to the black or the dark brownish crude from crude oil. But the similar refining process, but superior relative to that coming from crude oil. We're going to see later. These are Fischer and Tropsch. These are very simple chemistry. They take the syngas, hydrogen carbon monoxide on the catalyst surface. When it gets to the catalyst surface, the carbon and the oxygen will deassociate. Okay, can you absorb and deassociate, and then the hydrogen, and then you have a carbon-hydrogen monomer. The monomer start propagating, it can go all the way up to C100, C150. So you start from gas, you go to liquid, and then you go to solid. Why it works? Okay, if you do not follow, but where you are focusing, you are focusing on those areas. So when normally I give this talk to industry people, I ask them, hey guys, what do you think is wrong over here in this picture of Fischer and Tropsch? Okay? Anyone figure it out?
Cigarette.
Yeah, the cigarette. Okay, so Professor Halwa, you know the. Okay, he is next to his reactor, and his reactor is carbon monoxide and hydrogen. Okay, and he is lighting his cigarette over here. So if he is down, he will be fired, and you're not gonna have the Fischer and Tropsch. Okay, chemistry. That's overall. So this process, as simple as you can see it from the molecule level, when we see it at the surface of the catalyst, That's a reactor. That's one of type of reactors. That's in order to have this Fischer Tropsch. This huge reactor, you see the people walking around here. That's reactor from the manufacturing all the way to Doha. You imagine how they could transport this and they put it in a ship. That's board ship until it gets this reactor. The amount of water in this reactor is equivalent to the water in 3 Olympic swimming pools. Okay, and it weighed almost more than 2,000 tons. One reactor to facilitate this reaction. Why? Okay, this is the other type of reactor. This is shell reactor, multitubular. Inside this banks there is thousands of tubes, multitubular tubes, backbed reactor technology. So we can do it this huge way, we call it the liquid phase, or we can do it this way, what we call it the gas phase reaction, if we roughly assume it's a gas phase reaction. So let us see. This is a technology developed long time ago. In the neighborhood in Qatar, we have Shell, have the largest work plant, they call it the Ferrel GTL, as well as we have the Oryx GTL plant of Sasol. What we could do when we come to this Fischer Tropsch, this is developed in 1920s by the German. If we look around, you're going to see that we are talking about two different reaction media. And as a chemical engineers, we are very familiar, and I believe most of us chemical engineers, if not all. Am I right? Most, let us say. Okay? That's the differences between those two medias when we run the reaction around. So if we look at the gas phase reaction, yes, very fast. Okay, the gas can easily diffuse, and then I can separate the liquids because this reaction will give me liquid from the products, and the back bed is still there. When I come to the liquid phase, Sasol technology, the liquid phase, because the reaction is exothermic, help me to absorb the temperature. Everything will be fine. Catalyst makeup, whenever the catalyst is used, I can take it out and bring another catalyst in the process. I do not need to unback the reactor and then fill it back again, whatever. It's just a continuous process, part of the product separation, and then the reaction control, because it's a huge, I can control it, and the productivity could be high. Okay? But what are the major challenges? In each one of them I have problems. Here, how to control this heat management in the process. How to, if I have a problem with the catalyst, how I could remove it easily and bring it back. Reaction control. Here, mechanical design, and then also my catalyst is powder. When I separate my products, I have to be very sensitive, because the catalyst could leave with the products, with this wax. Okay, so it is more of complicated story. Do we have a room to solve this issue? The reaction media are different. It plays an important role in the reaction process and in the overall mechanism of the reaction. And if we need to develop anything new, we have to understand each one of them separately. And when we understand it, we understand everything about it. So if we assume that's a backbed reactor, I have to be capable of understanding how the kinetics of the reaction happen. If this reaction is highly exothermic, then it may form hotspots. How I will manage them so that it will not gonna break my products as I form. In the phase behavior, because I start with gas, I end up gas, liquid, and solid. Okay, how I manage to ensure that the flow of my reactors and everything is sustained. And now the most critical one and the most challenging one, what really happened inside the capillary structure of the catalyst. That this catalyst is formed of porous structure of aluminum or silica, and the active side, which is cobalt, is inside there. How I manage and how I understand this phenomena to maximize the benefit of it. So we have done a lot of research to do this, and that research well funded by industry as well as by funding agency in Qatar called Qatar National Research Fund. And then when we develop this technology, you have to scale it up. We have to prove that whatever other technology we develop is scalable in terms of design as well as in terms of economical management of the process, because here I can sketch it like this one, and then when I build my flow sheet for the actual bench scale, and then I need to make sure that it can go to a commercial scale. So many research work that has to be done in order for me to see the scalability of this technology, and we have worked in all of it. But also we work on when we get the products, those fuels, how we can handle them, how we can manage the process among them. And that's also well funded. I will give you an example here, just on simplifying that description. If we assume that this process happened in a conventional backbed reactor, okay? That the gas will come, will hit the catalyst bed, and then the reaction is stopped. And the gas will give me what? Liquid. Because we said that this can go all the way up to C100. And then the liquid will gonna start formulating inside my reactor bed. So in chemical engineering, we say the first layer will be a gas phase, the second one and the third one will be a trickle bed, because the liquid have to leave. this reactor bed. So in simple cartoon, carbon monoxide and hydrogen come. This is what happens inside the catalyst porous structure. The wax start forming. The wax fill the catalyst porous structure and then become liquid, completely filled, and then the liquid will gonna come down as a trickle bed behavior. Good deal? Now what is the problem? The problem is a mass transfer limitation in a significant portion of the reactor, because when this gas come, the one that's want to get to this layer, we're gonna find it around it liquid, and inside liquid. So the mass transfer limitation significantly impacting the catalyst effectiveness factor. So whatever they have right now in Shell, they are very proud of it. They will never say that there's something wrong with it. Okay, they have limitation in where really the reaction happening in their catalyst bed. Okay, then if we figure out a solvent and we say that we're going to mix this solvent with the syngas, and then the whole mixture will be a liquid-like medium, but not liquid. Okay, because liquid also is going to cause mass transfer limitation. Something in the near critical and the supercritical phase. That means it's still a single phase dominating by the solvent and the syngas. And this could really allow me to have a liquid-like density and heat capacity. I can control the temperature, gas-like diffusivity and transport property, as well as I can control the behavior inside my reactor bed, which is the advantage in the liquid phase, Sasol technology, and the advantage in the gas phase, Shell technology. And by maneuvering, playing with the pressure and the temperature, I can move it from a liquid-like property to gas-like property within the supercritical phase. I don't need to get anywhere of it. Okay, so how this will going to influence that reactor bed we have seen earlier? If that happens, then the solvent will going to come with the carbon monoxide and hydrogen, will mix, the reaction will happen, the wax will form, and you will see as the wax form, it will disappear. Because the solvent dissolved it. The solvent is the dominating one, and they will always have this two-phase regime, that the solid catalyst and this solvent that dominating the media, absorbing the products and the reactant, and will eliminate the mass transfer limitation and the heat transfer limitation, and that's theoretical. Now let us come to reality. If this happens, what the value it will gonna add to me? If I really manage to have such kind of environment, and I played quite well. First of all, one of the issues in this reaction is that most of the industry currently it allow it to go to heavy hydrocarbon, produce very heavy hydrocarbons. When it goes there, okay, they have to go and crack it back again and cut it to small pieces and they make the fuel. If I manage to do this inside the reactor, I can manage to have all of those products earlier, and I can do the separation earlier, and everything will gonna be fine, and it's gonna be a significant saving in terms of money. But also it will gonna keep me my catalyst active, because catalyst is not filled with wax. And then everything, the catalyst activity and also the maintenance of the catalyst and the regeneration of the catalyst in situ can be facilitated. So what we have done a lot of research in this area. As I indicated to you, we have to start with the porous structure of the catalyst. What happened inside? We have to start from the micro and then move to macro. Okay, so when we look around, we're going to see in each one of those, the liquid might fill it fully or partially. And then I could separate the products in the system. The more liquid I fill it, the less active site accessibility that I will going to have. Okay, so we need to measure this mathematically. That's what we know for a fact. Okay, and also we need to visualize it. Still, even Shell don't know exactly what happened in this. They fill it, they put flow in, flow out, they measure the product, they indicate, yes, that's the catalyst performance. So we collaborated with Cambridge, Professor Lynn Gladden in Cambridge, and we work with her because she has an NMR and MRI capability that's even in a cobalt catalyst. She can visualize in that environment how many phases will form inside the catalyst bed, and where is the liquid goes, and how the diffusion of those phases together. And that helps us to perfect our model. So our model is not based on only theoretical assumptions, on visualization of how this phenomena will happen at each one of those conditions. And that helps us big time, by the way, to model the reactor bed, because when we model it, there is so many phenomena associated with it. Mass transfer, heat transfer, and certain boundary condition in the system. And when we capture all of those together, and when you use supercritical phase, everything is not gas, is not liquid. So your conventional equation for the gas phase will not work. Your conventional equation for ideal liquid phase will not work. Then you have to figure out something else. That's a big even challenge in terms of thermodynamics. what is the most appropriate equation of state that could really capture those phenomena, and how to calculate effective diffusivity, because carbon monoxide when diffused in the wax is different from when it diffused in the solvent. So those parameters you have to measure them quite carefully, as well as the thermal diffusivity. So we measured all of those parameters, and we were able to see the profile inside these active sites of the catalyst in terms of concentration and in terms of the temperature. Okay, and that's helped us, by the way, to build the first phase on modeling this in terms of 1D modeling activities. Now the question will be, what will happen when I look at it further, not only the active side of the catalyst, the whole reactor bed. When I'm trying to model the whole reactor bed, now I have to look at so many other phenomena, because the hydrodynamic of the reactor beds will play a critical role. It's not only mass balance and heat balance equations, okay? And we have to capture it. And when we have done that, we were able to observe all the behaviors in the reactor bed that even mimic what we see in the experimental reactor units. We can see the temperature profile. When the exotherm of the reaction goes up, the temperature is going to go up in certain level, and then it goes down when the liquids come down from the reactor bed. We can see how the compression profile looks like, etc. Then we model it. Excellent. We have seen what happened in terms. Now we need to see what products we're going to get. Okay, this reaction can give me paraffin, can give me olefin, okay, as well as can give me oxygenate. But cobalt catalyst will only give me paraffin and olefin. And I need to see whether I could predict by model what will be the product profile. So we use our reactor setup, and we generate a lot amount of data trying to look at the kinetics and the distribution and the formation of each one of those products in the system. I have a PhD student. He was a master student. That's when he published this paper. But now he's a PhD student, Sheikh Afzal, working with Professor Al-Halwaji, and myself working, trying to understand a different topic that I will come later to. But he was able to measure that profile in the product's distribution. And it's very complicated story, by the way. He spent 1.5 years just working to perfect those models so that he can predict this dip. You see, this is the one of the most critical one in the Fischer Tropsch. When you capture it, you know that you could really manage a performance for a cobalt catalyst. And he predicted quite nicely the behavior of the reactor bed in terms of selectivity. Then he moved from a single 1D model to 2D model, working with Professor Ben Wilhite. Okay, and I have another one, Sufyan, and he's also now a PhD student, that his master work, but he continued on it as a PhD, trying to model this behavior in 2D, because then we can scale it up, because 1D will not going to help us to scale up, only to understand phenomena. To scale up, we need 2D model. So he have moved his modeling capabilities to focus on console simulations, and he managed to see so many phenomena inside the reactor bed. Now, earlier only we see axially, when we go from the top to the bottom. Now he can see radially how the behaviors look like in the reactor bed, how the temperature distribution. This is a lot of details. I know the time is not sufficient for me to go through them. As I indicated, guys, feel very free if you are interested in any of those topics. You can schedule a meeting. Professor Strat is very kind of us. He gave us an office over there, so I will be around here if you are interested in any of those topics. But now we able to see things radially as well as axially, and that's helped us to build our reactors. This, what we call it, dispersion because of the radial. The radial effect have effect in temperature distribution as well as in the mass distribution in my system over there. Okay, then this is when we look at the overall process. This Fischer Tropsch, as I indicated, is only one of the building blocks of the GTL. You remember? We said we have the gas generation, syngas generation, and we have the refining. It is in the middle. If you want to do something, you have to see the overall picture. This is one of the well-cited paper, in collaboration with Professor Al-Halwaji. He led us in this work with one of his former PhD students that I had the pleasure working with her as well, Bubing Bao. Okay? And this is one of the well-cited papers. If you go and you look at modeling of GTL process and integration of energy in GTL process, one of the leading areas, because even we inserted the possibility when we have the supercritical solvent, how that will going to change the overall energy. in the process, where we can get the solvent, how it looks like in terms of energy. Then we looked at the thermodynamics behavior of it in collaboration with Open University to understand where is this supercritical phase happening. Because supercritical phase, those chemical engineers knows it happens at the critical temperature, critical pressure, as well as it has value critical density. We have to observe it. So when we are vapor-liquid equilibrium, you see meniscus, liquid, vapor. When we are close to the critical point, this meniscus become hazy, like a cloud. And exactly at the critical point, what will happen? The meniscus disappears. So we can do it experimentally, take a lot of time, but we have done it experimentally as well as by modeling. And then we identify commercially what will be the best solvent in terms of the safety of the process and in terms of economic value. And we do not need an inner solvent that comes from outside. We use one of the products of the Fischer Tropsch. And we found that it is critical properties really matching what we need to make the whole thing in the critical phase. Okay? And then we looked how to separate the solvent from the system, how much energy that it really costs us. And we started work by Dr. Nuruddin over here, as well as Bubing Bao, and then continued this work and finalized by a master degree of one of my students, Professor Halwaji, also co-supervised her. She just defended a couple of weeks ago, and showing how to really get to this best optimum separation sequence of the process. Based on that, we developed a reactor technology, and this reactor technology has been patented. Okay, that's one of the sequence, that's the technology development. But now where we are going, we do not like these conventional reactor bed plants. And alumina, okay, supported cobalt catalyst. We are working on a different, we call it a frozen bed. We don't want the back bed or the slurry reactor, and this is we're working with Open University. Professor Fischer. He's building a mesh. We have the cobalt catalyst like this, not inside the capillary porous structure, and we manage, because of the thermal conductivity of this material, to dissipate most of the heat that's coming because of the exothermicity of the reaction. And that's a unique work in progress. But you have also my PhD with Dr. Will Hyde. We just working in a paper that hopefully you're going to hear a good news about it. Okay, that's almost progressing quite well, describing how to model such kind of performance. We have also tested in my reactors at Texas A&M Current. This is my reactor unit. So we build a bench scale. Now we need to move to a pilot scale, and we build it accordingly. So this is a complicated bench scale. I don't want to spend time on it. Now let us very quickly go into other topics. I'm not going to spend a lot of time on them. The refining, because we said we work in the Fischer Tropsch. Now when we get those products, what we do with them? How they are compared to those coming from crude oil. By the way, we call them ultra clean fuels because they do not have sulfur, they do not have aromatics at all. Okay? But this causes problem when it comes to aviation fuel. So Qatar Airways want a fuel that cleaner. Okay? And they have in the next to them the world's largest GTL plant. But they want to make sure that the aviation fuel they get from Shell in that plant can work in their airplane. Why? Because airplane fuel is not like transportation fuels, automotive fuels, am I right? There if you have a problem, you're going to get out and take a taxi or Uber. Okay? Here if you have a problem in the middle of the sky, I'm flying from Doha to Houston, then we'll be landing in France, am I right? So you have to make sure that your fuel is really perfect and works similarly to the fuel that's coming from crude oil. What are the differences between them? Our fuel is very neat, paraffinic hydrocarbons. Perfect, very high energy because they are paraffinic. And the fuel coming from crude oil have all of those components. So when you come and you try to develop this fuel, you need very sophisticated facilities. So we built in Qatar one of the world's best facilities in terms of fuel characterization. That's an ISO certified lab, by the way. All those companies use us. Shell, okay, Oryx, GE, Qatar Airways, they use us to characterize 30 new generation of fuels and fuel plants. Why those properties of fuel are critical? We do not need an engine lab. Those properties can give us a lot of indication. This slide borrowed from Rolls-Royce, from one of the collaborators that work with me in this project from Rolls-Royce. It tells you any of those properties you measure related to how the fuel will going to be combusted inside the engine, what type of emission that's coming out of the fuel, and how you control the characteristics of the fuel inside the systems. And I'm going to give you a very quick insight. The fuel is mainly paraffinic, that coming from GTL. In order for me to certify it in an airplane, so I can go to the Houston airport and I can tell them that fuel can work for you, its density have to be in this range. Okay? It is a freezing point, it's supposed to be in this range. Okay, and so on. The heat content in all of them. So when the one that meets all the specification is only this range. But the ETL one that Shell produce right now is over here. So our role as researchers, we either to convince those guys even this one can work, or to bring this one over here. And that's a very sophisticated research work. We're trying to understand how the fuel composition work with the characteristic that they are looking for. Sometimes linear, like density. The more cyclo, the better you get, but sometimes completely non-linear, like freezing point. Okay? And why it is non-linear? Because when you freeze your fuel, this fuel is composed of several hydrocarbons. You see, it freezes differently. Some crystals, some hazy, some waxy, etc. Why? Because the hydrocarbon structure, the iso and the cyclo pour point, and the phase diagram is different from each one of them. And why this critical? Because here, in the summer, the temperature can be 30 degrees Celsius, but when you get to 30,000 and 40,000 feet altitude, the temperature minus 60 degrees Celsius. So if this fuel is freeze, you are done. You will be landing. Okay, so you have to make sure that it's not freezing. And also we work on designing new generation of diesel fuel. And by the way, we use the diesel fuel that Oryx GTL get, that the plant in Qatar, that the program, and we prove that they can produce something even more valuable. This is a paper just in press. Okay, we're gonna show up, it's already online, okay? But also we develop new generation and fuel surrogate in collaboration with Professor Rafiq Ghani in DTU, and trying to see in the gasoline area. And that's the work we have done initially with GE, oil and gas, when we blend those fuels together. And for India market, by the way, the whole focus for this GE was for India market, and they funded us for it. Qatar, with all of what's going on, it started emitting a significant amount of CO2. Okay, all of those plants in and per capita, very small population, have the world's largest existing infrastructure in natural gas processing, and then they become a CO2 generator. So we took advantage of this. Okay, that's we are trying to see how we could integrate their CO2 in the map, and that's a $5 million project. That's we have a big consortium that's really was the huge success for the Gas and Fuel Research Center. This is one of the biggest success that we have. So we established a consortium in collaboration with Total, as well as in collaboration with Northwestern University and Texas A&M here, and Texas A&M Qatar played a critical role in developing this consortium and the lead BI of it, and that was the first success story. This is when we come to the reforming. You see? Now we are trying to insert this CO2 we are producing in the GTL process back again to produce more syngas. So we are trying to capture the CO2, but what is the problem with the CO2? Whenever I need to handle it, I need energy. And from where I get the energy? Fossil fuel. And if I burn fossil fuel, I produce CO2. So now my problem how to make this CO2 story, CO2 fixation. How I could really fix this issue. So whenever I tell them I will going to use CO2, I have to make sure that they understand that I will going to do it in a way that the more CO2 I put in the system, the less I will going to produce in the process. And that was the major challenge. CO2, when you put it in the catalyst, you have to protect it. So we design a new generation of catalyst. We design a new generation of process, and we make the case quite equivalent to Qatar. So we looked and we mapped all Qatar infrastructure. Okay? And we identify what the sources of CO2 stream they produce in each one of those plants. And if we capture them, what energy required. And if we treat them, and then how we integrate the syngas back again in Qatar infrastructure. So that's one of the biggest projects that global-wise we have Professor Tobin Mars here from Northwestern, a big group between Texas A&M. We are developing new catalytic systems and new reactors, by the way. This is just a patent being filed for this process, and that's also one of the students working on over here. So in summary, I'm so sorry I told you a lot of stories. As I told you, as it's like a movie. It's a quick story. But in summary, so we are trying really to establish infrastructure in a way to be a leading global center in the area of gas processing technology. We are moving to do many projects, but those projects require different building blocks and different collaboration global-wise. And now we are moving in the areas of advancing this CO2 reinsertion back again in the gas processing technology. So this work has been done in collaboration globally with so many people, and internally here in Texas A&M, I had the most pleasure that's working with many of the colleagues here, and that's the purpose of the center itself, that we are working together, and sometimes we are working in multidisciplinary team to ensure that all the points has been well addressed. But we work very closely with industry, by the way. Those are partners in a real project. They are investing time, they are researchers in those projects, besides the funding that we received from industry in those projects, and those also we formulate that kind of global collaboration. This is part of my research team in Qatar. So that when it started, 2009, 2012, and now, okay, and we have more of them. That's and specifically those in Texas. Normally they are here. We cannot take photos of them. Those are the PhD students. So finally, I have to acknowledge Qatar National Research Fund, MOSIT, and the industry shell, Oryx GTL. They have funded a lot of those projects, as well as the TEAS Gas and Fuel Research Center and the Oryx GTL Excellence Program over here. Thank you so much for your patience.